Just, well, good day and welcome to Society, Robots and Us. It's been actually 2 months since our last one. This is an event that, well, we started it actually right at the start of the pandemic as an opportunity to say, well, what is happening and how does robotics fit into what is happening? There are some really big social changes. And robotics, is it living up to its potential? If not, why not? Where is it? How can we share this information? What is happening? And as that urgent aspect had, so we were actually doing this event on a weekly basis for a couple of months. And as the urgency diminished, and well, firstly, it was also very clear that robotics was playing a strong assistive role in parts of the pandemic. And we were lucky enough to have Robin Murphy talking to us, and Professor Robin Murphy is at Texas A&M University, where she very much founded the field of rescue robotics. And she's been tracking how robotics was working in different aspects of assistance for the pandemic. And that really started a seminar of inquiry from that point onwards as to the role of robotics in society. And in the course of a number of really interesting episodes where we tackled subjects like robots and racism, killer robots, robots and gender, robots and agriculture, it became clear that inclusive robotics was a topic that was very, very dear to many of the speakers, and particularly to Professor Ken Goldberg and myself, who've been running this seminar. And we've started to circle in on what does inclusive robotics look like. We need to take a broad perspective because it's impossible for inclusive robotics to have just one flavor or to be important in only one aspect of robotics. At the moment, a really good way to look at inclusive robotics is to say it is both a process and it's a product. And as such, we've had some interesting discussions around robot exoskeletons, powered clothing, robotics technology for elder care. And tonight, it's a real pleasure to have David Jaffe, who has been teaching assistive robotics for many years at Stanford as a speaker. He wasn't able to join us the last time we were talking about this, and he's been able to join us today. So I'm very pleased, particularly because he's going to have a longer time to explain, well, as much as he can squeeze what is an entire course into a short seminar, but we will have the benefit of learning about assistive robotics. We'll also have the benefit of hearing from Carmel Majidi from Carnegie Mellon University, who is in the soft machines lab. And I believe that soft robotics is a transformative technology for not just assistive robotics technology, but really human-centered robotics technology. And so I'm very much looking forward to hearing perspectives together. Now, both of the speakers will get a little bit longer to talk tonight because I'm afraid Tanya's unable to join us and Ken has just gotten sick and is unable to join us. So that is great for having a longer time with our two main speakers, and also for everybody in the audience who has questions. And the usual procedure for questions is please put your questions into the chat, and our speakers will respond either directly or in the chat. And if we have time, then we can have more of an active conversation. But at any stage, if you have questions, put them into the chat and we'll see how we can respond to them. And we're recording. So I just want to make sure that everybody knows that there'll be a recording going up on YouTube in maybe a month or so. It can take me a little while to get the recordings tidied up and up there. We have almost all of the Society Robots and Us recordings on the Silicon Valley Robotics YouTube channel. So I really do encourage you to go back and have a look through some of the ones if you've missed the episodes. And I think almost all the up-to-date links on the Eventbrite. And well, let me just say, I'm Andra Keay. I'm the Managing Director of Silicon Valley Robotics. I'm also a visiting scholar at the Citrus People and Robots Lab with Professor Ken Goldberg. And it's my pleasure to do a lot of work both with robotic startups and with the topic of, I guess, robots in society, ranging from impacts to looking at things like the equity issues. So if you're interested in joining, for example, joining me in Women in Robotics, or if you would like to be connected to the new group Black in Robotics that's formed since we did the episode on robots and racism. So we're working at a grassroots level to empower everybody in robotics as much as possible. And so my final statements before I hand over to David is to acknowledge that I'm personally speaking on the lands of the Mwukma Ohlone tribe, who have not been federally recognized as an American indigenous tribe, but were the first owners, first custodians of the land here. I'm still a little bit Australian in my terminology, so many apologies if I've used the wrong words, but I've been pleased to see more countries acknowledging some of the areas in which we've not done the right things and our technologies have not yet had a positive impact on redressing those issues. And that's really at the heart of why we're having these discussions. What does it take for robotics, a technology with so much promise to do good in the world, to live up to that promise? And so I'm really pleased to hand over to David Jaffe now.
Okay, let me share my screen. You're seeing my slides?
Perfect.
Oh, okay, great. Yeah, thanks, Andra, for inviting me to participate. My last name is Jaffe. I'm a lecturer at Stanford University. I've been there for 15 years, and prior to that, I was at the VA hospital in Palo Alto, where we had a rehab research and development center where we did all sorts of interesting stuff on devices, high-tech devices that would benefit veterans with disabilities. And let's see, my background is degree in electrical engineering from Michigan, biomedical engineering from Northwestern, and now I find myself at Stanford. So I want to talk about a variety of topics today. And I'm glad I have a little bit extra time because that takes a little bit of the pressure off. And talk about some projects we worked on at the VA. Talk about the course I teach at Stanford, and talk about disability, assistive technology, and a little bit about the design process. So I started at the VA in around 1980, and in early 1980, we had a lot of projects, and there's three robotics projects shown here. And maybe let's start on the right. This is a robot station where you see this Puma 260 robot arm hanging above a desktop, and it's on a track here. And this is a user who is a quadriplegic, and he uses the robot to help him in his daily activities. And these are typically this one is set up to be vocational. And you see here the robot is handling a video disc. Remember those? And it could also pick up floppy disks and insert them into this Mac computer over here. So used voice recognition to move and perform tasks. And that required these things that were being interacted with, like a phone and other things to be in a specific position. The user used a mouse stick to move the trackball here. We also had a version of this that was able to do tasks like putting soup in a microwave oven, turning it on, closing the door, and actually do the feeding application. This middle project is one using a larger Unimation arm, and it's used as a therapy robotic device to help people who are stroke survivors gain a little bit more strength in their upper extremities. And so we worked with a bunch of people to help them out. On the left here is another one of these Unimation arms mounted on a mobile base. And the interesting things are these omnidirectional wheels, which we did at the VA. This whole thing was controlled wirelessly from a remote station using voice commands and also head commands. And it had an LSI 11 in it, programmed in Pascal, and it's sort of dated by this Tandy DOS laptop over here. Here's a couple projects that I worked on, and I'm not going to play the links. I'm going to put them in the chat so you can view them at a later time. This is a power wheelchair for people with quadriplegia who don't have use of their arms, and it employs a couple of these ultrasonic sensors to range the distance to the user's head. And as the user tilts their head forward, backward, left, and right, those positions are picked up by the electronics and actually operate the wheelchair. So you can think of it as your head as being on top of a joystick that would normally control the wheelchair, but in this case, it's all done wirelessly. And that's going to have its 40th anniversary pretty soon. So that worked out pretty well. This is a more interesting robot. This is a tactile robot that doesn't do manipulation. It actually is a communication device. And as some of you may know, there's an alphabet for people who are deaf called the Fingerspelling Alphabet. And when an interpreter for the deaf gets to a word for which there is no sign, it's actually spelled out. In this case, this is the letter V. This unit is connected by a cable to a keyboard. And as you type the letters of your message on the keyboard, the hand moves to that finger spelling position, and the deafblind user would touch this hand and interpret letter by letter, what the message is. So this is called Ralph. Again, probably done late 1980s. So I'm now going to talk a little bit about the course I've been teaching for the last 15 years. It's called Perspectives in Assistive Technology. It's taught in the winter quarter, which is beginning in January, and all the courses are 10 weeks. It consists mostly of guest lectures. We do field trips when we're all meeting together, and the students work on projects. And I'll get into this a little bit more. So this is the key question I ask the students. How do you know that the education you're getting at Stanford is really relevant when you get out into the real world? well, my course is an attempt to do that, and I'll explain why. The objectives of the course are just to gain additional engineering confidence, although not all the students are engineers, others are in other disciplines. Its focus is on critical thinking, communication skills, working in a team, and working with people in the local community, as well as learning about all the good things about assistive technology. And it gives students, a chance to practice their leadership in organization and problem solving. Um, so yeah, problem solving is sort of a key issue. The students work in a team, typically 3 students to a team. They work in the community and they address challenges experienced by people with disabilities or older adults. And so this is a real life experience, and it's called public service and service learning. And the key part of the process of the project is going through this process, which I'll describe a little bit more. It's a good process for the course and addressing engineering type problems. Key element in the course is communicating. And I remember when I was a student in engineering, nobody told me how important report writing and during oral presentations would be. You think about being an engineer and working in a lab, when you graduate, but you actually spend a lot of time, writing reports, grants, and doing all sorts of presentations like I'm doing now. So it's a very important skill to have. And of course, in any of this stuff, you have to have leadership, and because Stanford graduates are expected to be leaders. So the course is about technology and people, assistive technology, the engineering design development process, partnering with the local community, and in that sense, it's actually a preview of professional life, solving problems, working with people. So it works out really well. So this is from last year. So there's some things that are crossed out here because it was taught online. So yeah, so the course is about guest lectures. We do field trips, a film screening. I have an assistive technology fair that actually worked out really well online. Lots of opportunities for questioning, thought, and reflection, and the project experience, which involves fabrication and other things. And for students who are working on a project, they review the project descriptions, which I get set up in place before the class starts. The second class session is pitch day, where the people who suggested the projects pitch them to the students. The students select a project, select team members, and then they start on the project and investigate the problem with the individual with a disability. So they actually interview and observe them in order to understand the problem, which I'm going to talk about a bit more. You need to understand the problem and gather information about what the problem is, and you use that to brainstorm and to come up with a design concept, which you prototype through several iterations of refinement. And at the end of the quarter, students present their design and demonstrate their design in class, and also submit a final report and reflect on the experience. So these are some of the titles of the guest lectures from last year. It's a variety of topics. I thought this was the best way of teaching the subject because, teaching it disability by disability or assistive technology by assistive technology gets to be pretty boring. So what I've done is I've identified people in the local community who are excellent presenters and who have the ability to talk about really interesting topics. And so these are some of them. We have exoskeletons, prosthetics, aesthetics, design. The one that gets a lot of attention is I just invite Stanford students with a disability to talk about themselves and in class, and that's the one that students like the most. Yeah, we typically have a field trip to the Magical Bridge Playground, which is a set of playgrounds in the local area here that are designed to be accessible and inclusive for everybody. And we also go to the VA Palo Alto and check out their spinal cord injury, where we talk to a physician and check out the recreational therapy and all the devices that they have for veterans. And let's see, yeah, more exoskeletons and prosthetics. We had a talk on virtual reality, and I had a couple talks on wheelchair fabrication in developing countries. That's always an interesting guest lecture. So students work on these projects, and here's a few from this past year. Students worked on these projects individually because they were scattered all over the world. Brian worked on this project to put legs on a camping cot. It actually takes a lot of effort to bend these in the right way, to stretch them across the cot. And so he has a linear actuator here so that the woman, Abby, who doesn't have a whole lot of strength in her arms, can put together her cot when she goes camping. Austin is a student at Stanford. He's a paraplegic, and he wanted students to look at designs that would help him do food preparation. And these are the two designs that students came up with. There was 3 students who worked with Tilly, who is a wheelchair user. And on the bottom here is her description. And these are the 3 results. These students 3D printed their prototypes. This one is pretty interesting because as the phone is pushed down, the side bars come in to lock the phone in. So very, very interesting design. A little bit about disability. So, I have to talk about disability in class, and you have to define it. So this is my inclusive definition of disability: is any situation that prevents an individual from taking full advantage of their talents and opportunities. That includes things as, the political system, because you're not going to take advantage of the opportunities if your planet is at war. So, yeah. Gregor has a very good quote. Disability is a normal variation on the human condition. And I thought that's a great description. Here's some numbers about disability in the US. You can read these on your own, but it's interesting to note that over 12% of Stanford students actually are registered with the Office of Accessible Education as somebody with a disability, not necessarily a physical disability. It could be a learning disability or ADHD or something else like that. So there's actually a lot of students with disabilities at Stanford. So here's the question I talk about, I pose in class. Identify a large group of individuals who spend many years in institutions before they can contribute to society. And of course, the answer is students, because, think about how long you've been going to school, from maybe pre-kindergarten to graduate school, getting a PhD, et cetera. That's a lot of time. And if we only had this technology from the Matrix, where you can learn to fly a helicopter in 20 seconds, that would make a big change in the educational system. And rather than talk about disability, let's talk about ability. So I came up with this chart to sort of track ability over one's life. And you start out as a kid being totally dependent on others. I'm not sure you call it a disability because everybody is like that. But as you grow old, you learn how to walk, to balance. Riding a 2-wheel bicycle is sort of a key milestone. Driving a car, learning cursive are all key points in a person's life. So it's important to note that people with disabilities are people, and that's the inclusive way of thinking about things, because, even the US Constitution starts out with a very inclusive statement. We the people, it's not just, certain people. And we talk about this because we use what's called people first language, because you name the person first and their condition second, because they are people first, and the disability is a secondary or tertiary attribute. Not everybody feels like this, and so it goes back and forth a little bit about if this is the best way to describe people. But when I describe people, their disability is the last thing I mention. So we've had relationships with people with disabilities throughout our lives. My first person with a disability is Captain Hook here, who is not using a real hook. This is a real hook over here, and Pinocchio is another one. Wizard of Oz. There's all sorts of films that have people with disability in them as major characters, and that still goes on. Every year I list new people that have identified as people with disabilities, and here are two from last year. And even superheroes can have a disability at some times. And I think there's some of the X-Men that use wheelchairs as well. So it's not just for normal people or non-superhero people, but superheroes can have episodes of disability as well. A little bit about assistive technology. So assistive technology is not just devices, but it's also services, policies, institution, the process that makes assistive technology available to people. And with this definition, even a service dog is a piece of assistive technology. And there certainly are computers that and programs that help people with disabilities. So these assistive technology devices provide greater independence, increased opportunities for participation, and improved quality of life for people with disabilities by enabling them to perform tasks that they were formerly unable to accomplish or had a great deal accomplishing or required assistance through an enhanced or an alternative method of interacting with the world around them. And then I was thinking, yeah, boy, I use a lot of devices that have the same definition. I'm using, my computer, the internet, Zoom, and stuff, and I couldn't do that, if I didn't have them. So that leads me to believe that everything is assistive technology, because, as Carl Sagan says, we're such puny creatures. I mean, we can, maybe run, walk at 3 miles an hour, or run at maybe 20 miles an hour for a short time. But we really rely on our technology: airplanes, cars, communication systems, science, medicine, transportation system, and the number one top piece of assistive technology is Stanford University. I change this out depending if I'm talking at another university. Like if I'm talking at Berkeley, I'll swap this out with their icon. But everything is assistive technology. Lots of people with a disability in the world, over 1 billion. But all these, it's not just homogeneous people. They're actually divided into groups and fragmented to the point of individuality. So there's, because people are individuals, and each person has their own unique personality, challenges, circumstances, goals, and aesthetic preferences, which means that, you can't have one wheelchair that works for every person who needs a wheelchair. In fact, I've never seen two wheelchairs set up exactly the same way. So this lack of a well-defined mass market means that companies serving people with disabilities and older adults are small, and their products are expensive, because you just can't make 1 million of them and expect to sell them. So you've seen a lot of stuff on TV about mind control limbs, brain-computer interfaces. This was on 60 Minutes. Elon Musk is working in this area as well. So in this, you can consider this person is controlling a robot through just thinking about moving it. And I think this woman can actually control 2 robot arms at the same time, which is pretty amazing. There's robots that are prosthetic hands. These are pretty much toy devices that makes kids look cool, but probably not functional or durable. We're talking about robots. You have to talk about transformers, and here's a bed that transforms into a wheelchair. And I just researched this again for somebody because the problem here is transferring from a bed to a wheelchair. If you're a quadriplegic, that might be really difficult, require other people. But if you have this kind of wheelchair, you can do it on your own. And there's a couple companies making these things, and there's even one coming out of China that I saw. Assistive technology isn't just for people. If you really need if you really want to get a sympathy for animals, watch this PBS Nature program. Just search for Bionic Pets, and so we have prosthetic limbs for elephants and mobility device for a pig. It's awesome. Here's an assistive technology device. You could consider it a robot, I guess. This is the Ibot Wheelchair. It's sort of invented at the same time as a Segway. These are no longer being sold because at $25,000 a piece, they were losing money on each one. Local company, Toyota Research Institute, was going to revisit that project, but I think they closed it down. But there is a company called Mobius Mobility who is making this kind of device, wheelchair device. So it allows you to go upstairs and go through rough terrain, outdoor terrain, and stuff like that. But it's unclear if you only have one wheelchair, would you want to have this wheelchair? Don't know. Here's another really interesting wheelchair that's been very popular called the wheelchair. And interesting points on it are these omni wheels in front, which eliminate the need for caster wheels. It's relatively inexpensive. I guess this model around maybe $2,500. Here's a close-up of the omni wheels, which provide the ability to roll along these rollers. At the VA, we worked on the Alexis wheelchair, which used 3 of these in a configuration that allowed the wheelchair to go sideways. So whether or not that's a feature you want to have, unfortunately never made it to market. Design process, is a last topic area. So the design process is a plan of action to achieve a goal, and it's a structured project. And the idea is that if you follow this process, you have increases your chances of success, and if you're a student, it increases your chances of getting a good grade. So the one core feature of this design process that I advocate is understanding the problem. Now, this seems to be so obvious, but a lot of cases it's not done. You really have to learn as much as you can about the problem, because the more that you know, the better your solution will be. And this would be a prerequisite to brainstorming. So if you were trying to solve a problem for a person with a disability, you would interview and observe them. You would talk to their family, caregivers, to find out more about the problem, maybe get a background on the user, what their goals are, what they really want to do, get a basic understanding of the health condition. If they're a quadriplegic or paraplegic or have a stroke, you need to know about that health condition. You want to work as a team, with with engineers and your users together, and also bring in other experts to give you some background. Because if you don't have this information, chances are that you're going to copy what somebody else has. And sometimes the only problem is the lack of awareness of an existing solution. People with disabilities don't really know the extent of what's available out there, and there may be a solution out there that they can use, but they just don't know about it. So, as an engineer or a designer, you want to check out what's currently available, and if there is something available, why doesn't it work? Why isn't it a solution? And maybe these existing products will inspire a better design for you. Another key process issue is identifying the problem. It's good to have a concise definition of the problem without, thinking about the solution. So here's the example that Austin gave about his problem. And again, here's the solutions that the students come up with. So, the students, might have a background in engineering, whereas Austin doesn't. So the user it may be tough for them to describe how to fabricate a solution that would work for them. So it's good to have this written down so you can refer to it. Design criteria is another part of the design process. Basically, you want to characterize the solution. What should it do? There are two elements of it, things that it absolutely should do to work, and other things that you can think of as icing on the cake, things to add at the end if you have time and budget. And you really want to not to forget the aesthetics factor and also the coolness factor. So coolness is a really important design criteria, because people, even if they're older or have a disability, they all want to be cool. And I picked up out 4 people that I consider cool, and your list may vary. So yeah, commercialization is the last thing I want to mention. It's a really difficult process because it involves a lot of time and a lot of money and good luck. And it's really tough in assistive technology because you're basically not doing mass production, you're doing customized production. I talked to a woman who was with an exoskeleton company, and I asked her, how many of these exoskeletons do you have on the shelf? And she said none, that they build them as needed. So, so it's a custom built thing. Even though there are a lot of users out there, the demand, you don't know what the demand might be. And students always talk about, gee, my prototype only cost $100. So if this were available commercially, it'd be pretty inexpensive. But I tell them that the price of a product includes elements other than parts cost. So that's about all I wanted to talk about. And I can take questions at an appropriate time, and I'd be certainly happy to talk about these things with you, given the time.
Thank you so much, David. And you really covered the topic very comprehensively. And I'm thinking that it was a really good transition to Carmel in terms of perhaps the solution for individualized customization is really where the promise of soft robotics lies. But I totally agree with you that it's far more than simply the materials. It's around the servicing, there's so much more in the commercialization. I saw some really good comments as well into the chat and some questions, but I'd like to ask Carmel to speak now, and we'll continue with the question and answers in the chat for the moment. So over to Carmel Majidi from Carnegie Mellon. It's Soft Robots, the Soft Machine Lab, I think.
That's right. Thanks a lot, Andra. Thanks, David. Excellent talk. As Andra said, I'll be discussing progress in this field of soft robotics, and a lot of what you see will tie into a lot of the themes that David touched on. But I also kind of wanted to give a kind of a broader historical perspective as well. So just, you know, starting point here, of course, is this robotics generally as a field. I mean, yeah, I mean, I think it's pretty obvious that a lot of the kind of the existing hardware and machines are incredibly powerful, incredibly precise, and very well designed for what they're intended to do. For say manufacturing, industrial automation, but for a lot of the emerging applications that David is talking about in the assistive space, when we talk about human-centered machines and technologies, a lot of this same hardware isn't quite well suited to the task at hand. And this is actually not a new problem in robotics. In fact, you could almost argue that this challenge of human-centered robotics really dates back to the inception of robotics as a field. And this is something that a lot of the early pioneers in robotics and then certainly soft robotics encountered. Here's one really nice example. Joe Mckibben was a physicist who's probably most famous for being one of the leads of the Trinity project for the nuclear program during World War II. And then he actually was the trigger man who detonated the first test of a nuclear bomb. As the war was wrapping up, and he kind of transitioned away from the nuclear program, he directed a lot of his efforts towards building an assistive device to help his daughter Karen, who was suffering from polio and had very limited motor abilities, and in particular with her hand and manipulation and grasping. And so what Joe did was, using the technologies of the time, created this soft hand exoskeleton to assist, so that Karen could wear to assist with dexterous tasks and grasping. Now, to build something that could be lightweight and comfortable to wear, Joe used basically an artificial muscle technology. And today we call this the Mckibben Actuator. Although Mckibben himself had not invented it, it was actually something that had been independently invented in France and Germany. And here's just a sketch here from a patent from around that time and from an inventor in Cleveland, Ohio. But basically the concept was quite simple. It's a rubber bladder with a braided fabric mesh that contracted much like a natural muscle did when inflated with compressed air. And this concept of a pneumatic artificial muscle or an air muscle really laid the foundation for decades of soft robotics research to come. And so this is just kind of one embodiment of these pneumatic air muscles. This is a really nice review paper here that came out in the early 2000s that covers other types of pneumatic air muscles that have all different types of form factors and in geometries, but still use this concept of soft materials and compressed air to create these very lightweight and naturally compliant actuators that match a lot of the features of natural human muscle. And so here's an example from back in the 70s, I believe, of the Robotuator. This is a robot arm that's composed of multiple Mckibben actuators that are used for robot arm manipulation and also grasping. And this is another really nice implementation. This is from a group in Japan led by Koichi Suzumori, who created a version of these pneumatic soft actuators that dispenses with the that braided fabric shell and allows for actuators that are much more versatile, much more robust, and allow for all these different modes of deformation. So I'll kind of skip ahead through this video. This is something you can find on YouTube, but it really kind of captures what actually to some extent still is the state of the art in soft robotics. So in spite of being, these videos being from the late 80s, early 90s, a lot of these concepts you'll still see today in a lot of commercial soft robotic products and also a lot of the academic research within this space. And just to give you a sense of how potentially powerful these soft actuators can be, there's a really kind of a nice video clip here showing the soft robot gripper unthreading a screw. So I'll just kind of skip ahead to that here. So with these soft robot concepts, it's possible to create actuators and technologies that on one hand can be soft and compliant and compatible with the human body, but can also change stiffness. They can become load bearing and capable of doing some pretty significant mechanical work, and hence the role in assistive robotic devices. So in the United States, a lot of the renewed interest in soft robotics has been spurred by investment from the National Science Foundation and also DARPA, which launched the ChemBots program in the late 2000s. So this is back when I was a postdoc, and this kind of supported a lot of the early work that I did within this field of soft robotics. And really the vision there wasn't so much to create soft robotic systems for human motor assistance, but instead to create autonomous bio-inspired robots that had abilities, say like an octopus, or some soft marine organism, where it could kind of squeeze through really confined spaces or tight holes. So the vision here was to kind of create a machine or a robot the size of, say, a soda can that would be able to kind of squeeze itself through an opening the size of a US quarter. And so early on, there was a lot of really tremendous work in the space from research labs throughout the country. And then in parallel, there's also similar initiatives in Europe and also later in China as well. So really internationally, we've seen kind of a tremendous amount of research in this space. Some of you might, for those of you who are familiar with the field of soft robotics, might be familiar with this implementation here. Very simple soft robot that actually ties into kind of another aspect of inclusivity that Andra had been talking about at the beginning. Really, the significance of soft robots are not just to create machines that are mechanically versatile and robust and are compatible with the body. It's also these platforms are kind of used as a way to democratize robotics, and this is really what was the motivation and driving kind of force behind the vision of George Whiteside's and Rob Shepard and other folks who kind of created these very simple kind of soft machines, just simply out of just taking rubber and casting it over, in kind of machined molds or 3D printed molds. And so within, just a few hours, anybody with fairly limited resources could, say, in their home, with, without, needing access to incredibly sophisticated equipment, create these soft machines that could kind of move around and achieve these kind of lifelike type motions. And so that kind of represents another motivation for this field of soft robotics. Here's some examples from my own lab. So a bit of a shameless plug, but this really is meant to illustrate here that we can build robots that are actuated with mechanisms other than using pneumatics and compressed air. All these are examples of untethered soft robots that are powered using shape memory materials. In this case, we're using a shape memory alloy. It's an alloy of nickel and titanium that can actuate in response to electrical stimulation. So those were just some examples of untethered soft robots from my lab. And then there's been, like I said, this is really an international effort at this stage. And so there's been all sorts of other implementations of untethered soft robots by groups around the world. And they use a variety of different types of methods for actuation. So we've talked about pneumatics, we've talked about these shape memory materials, but there's also electrostatics, light activated electroosmotic stimulated material actuators. And also recently, there's been a lot of exciting work in using natural muscle tissue. So using tissue engineering to harvest soft actuators that combine natural muscle tissue, say like cardiac cells or skeletal muscle, with soft materials like silicone rubber. Also, there's been a lot of really exciting work with creating assistive soft robotic devices that are powered just using conventional motors. And so a lot of these electric motors didn't exist, during the time of Joe Mckibben, back when he was building that hand exo for his daughter Karen. But over the subsequent decades, there's been a lot of nice progress and miniaturized servos and DC motors, and we've seen a lot of really nice work using those technologies as well. So along this theme of assistive soft robotic technologies, this is a really nice implementation from Connor Walsh, who's a roboticist at Harvard University, where they've used kind of a variation on that Mckibben actuator, actually a little bit more similar to that those soft actuators developed by Koichi Suzumori's group in Japan. And here again, you can see, because we're using soft materials, because we're using compressed air, we can create these assistive devices that are comfortable to wear and can assist motion without really kind of, overriding or kind of unnecessarily constraining the fingers and the limbs. And then let's see if this video will play. This is a nice example of kind of a effort towards incorporating soft robotics into minimally invasive surgery. So this represents kind of another really exciting direction within the field. And I would say that this, even though this video here is just from 2014, this idea of using inflation, compressed air, soft materials in medical operations has existed for decades. I mean, for those of you who are familiar with balloon angioplasty and you'll kind of in different types of balloon catheters, you'll kind of recognize these concepts in a lot of these more conventional medical operations as well. But here, an interesting feature of this the soft robot catheter is that in addition to being able to kind of deform and conform to kind of the curvature of human organs, it also has this stiffness tuning effect. And that's kind of another really important feature of soft robots. And that kind of helps them overcome this kind of paradox where soft materials by themselves are very compliant, highly deformable, not really capable of bearing a lot of mechanical load. But if they're able to change their stiffness, then they can adopt configurations when they can be load bearing and capable of exerting mechanical work. And that's also a feature of our natural muscle, and then also hydrostatic muscle or hydrostats, hydrostatic skeletons, and a lot of other natural biological tissue that also exhibit stiffness tuning properties that allow them to change shape, but then also become load bearing and exert mechanical work. So a lot of really exciting progress. From an academic perspective, there's been kind of this explosion of interest that did coincide with those initiatives by DARPA in the late 2000s, as well as the RoboSoft program in Europe. But a lot of these kind of more recent accomplishments do build on concepts that have existed for decades, dating back to that original work by Joe Mckibben. So along with this kind of recent rise of interest in soft robotics, there's been all sorts of international workshops and conferences, peer-reviewed journals dedicated to the field of soft robotics. And I want to spend a few minutes talking about kind of other aspects of this kind of growth in soft robotics. And what I've found most encouraging is to see this fairly rapid adoption of soft robotics within industry, not just with larger established companies within robotics and manufacturing, but also startups. And so there's been a lot of really exciting work and progress by startups that have ties either to academia or kind of come from other communities within industry. So recently, there's been market studies looking at soft robotics as a emerging industry and looking at forecasts for how this industry will grow in the next few years and decades. And a lot of these companies are included within these market forecasts have worked in robotics for some time, and others are fairly new startups. And so of this big list, you have companies like Festo that have been developing pneumatic actuators for decades. But then you'll also have out of UC Berkeley, you have Exobionics, a spin out, creating these assistive exoskeletons. You have also Cyberdyne that's also made a lot of progress and really nice advancements in assistive robotics. And then there's also this nice kind of a growing community of startup companies that are incorporating soft materials and soft robotics for industrial automation, and particularly in working with very delicate materials. And so Soft Robotics Inc. is a spinoff from George Whiteside's group at Harvard University that's done some really cool work in this space. And so just a few videos here. This is from Festo. I think probably the world's largest manufacturer of these pneumatic air muscles. And they've done a lot of work both in-house and also in collaboration with academic labs, building some really nice soft robot implementations that not just use their pneumatic artificial muscle technologies, but also incorporate soft electronics and these tactile skin type sensors. And so really nice, beautiful, highly integrated soft robot implementations in this case for a biomimetic soft robot hand. So I'll just kind of skip ahead through this video here. And again, a lot of these videos, you can find on YouTube. And so, yeah, really nice implementations coming out from Festo. And then I mentioned Soft Robotics Inc. And let's see if this video will run. But they've partnered with a lot of companies in industrial automation to create soft robot end effectors that are capable of manipulation and grasping and performing pick and place operations on very delicate objects. And again, the ability of these end effectors to handle delicate objects arises from the fact that the end effectors themselves are made out of soft, compliant materials and are powered with air, and so also very lightweight. So I'll just wrap up here, just a quick shameless plug. I mean, part of the theme of this session is also on hiring. And so, as I said, there's been a lot of different university spin-offs in the space of soft robotics. My own group has had former PhDs and postdocs who have launched companies of their own. So one of these is in the healthcare space. So these are kind of like electronic stickers, like you can see to the left, that are soft, flexible, stretchable, fully wireless, capable of physiological monitoring. So this is a spin out from Carnegie Mellon, and we are looking to hire. So anybody who is interested, we are looking at hires kind of in different capacities, from business development to experts and kind of on the machine learning and data sciences side to mechanical engineers. Likewise, we have a company more focused on novel multifunctional materials that can be used in soft electronics and soft robotics. And here also we have a few openings. And then a more recent spin-off company from the lab, founded by a former PhD student, has been developing lightweight actuators and clutch technologies that can be used in exos and mobile robots. And also they're looking to hire both folks in business development and also in mechanical engineering. So definitely reach out. You can easily find find me online, find my email. Just contact me if you are looking for opportunities within the space. And just lastly, as I said, I mean, there's forecasts that have predicted the potential for tremendous growth within this field of soft robotics. So currently, the market is kind of under $1 billion, but that's expected to grow at a rate of about 40%. So I expect a lot of hiring within this space. And I really do want to emphasize here that the types of folks that and the types of skills needed within the space really kind of span the full spectrum. And so, everything from mechanical engineering and materials to kind of more, traditional robotics, computer science to human psychology, to, you mentioned, human-centered design, and that kind of is a whole discipline and field in and of itself. And of course, also on the business and commercialization side as well. So a really rich opportunity here. So I think we're kind of at 10 o'clock, so I'll just kind of quickly skip through this. But soft robotics, although it's been around for decades, now is kind of a timely kind of opportunity for there to be growth in the field because of the confluence of progress in a few different disciplines. And so the outlook is pretty good, but time will tell to see if the field will truly kind of fulfill its potential, or if it's going to remain just kind of more of an academic field. So with that, I'll wrap up, and yeah, please do reach out to me by email if you have are interested in kind of any potential hiring opportunities, and also happy to take questions now.
Thank you. That was an amazing presentation. We've had two fantastic presentations, and I am now convinced that I need to make sure that our speakers have a long enough time to give a thorough presentation. Well, really, I know you just whetted our appetites, but you both very successfully whetted our appetites. And I definitely think that commercialization is a topic that we need to follow up with, because I've spent quite a while talking around the commercialization of soft robotics with Soft Robotics and some of the other startups in that space. And I've been surprised in a sense with how slow it was, but when you're deploying an end effector, it has to go onto a robot arm. And in many ways, the robot arm industries itself are slow moving, comparatively speaking. Effectively, the promise of soft robotics is opening up in so many new industries. So you're having to do the entire, I think, business development for automation, not simply for the end effectors. And I do think that that's been a slow threshold, but that the estimates of the growth for the next decade are much lower than we'll actually see. And I want to bring in a few of the investors who specialize in deep tech, science-based startups, particularly around these emerging areas, so that we can start to explore some of these issues, including the issue that David raised right at the start, which is when everybody requires a unique product, how can that possibly be cost effective? And, perhaps we're starting to look at ways of developing customizable products. I know that was a point that Tarun raised. Are we seeing that kind of customization in assistive robotics technologies? But Oren has got his hand up. Oh, and I see he's put his email in there. He would like to be hired. Did you want to say something directly, Oren?
Yeah, I think this will be Carmel. You showed a lot of different really amazing robots, and I'm kind of curious, like, what is like new? There's a lot of like stuff that's probably iterations on previous ideas, but like, is there any like new modes that you've seen that you're excited about, or stuff that's like, wow, that's really cool that you want to pick out of that swarm of stuff?
Sure. I mean, my kind of interest has kind of long been in kind of bio-inspired engineering and biorobotics. And so, anything that's kind of a new material, a new actuator, a new sensing technology, that always kind of strikes me as really kind of interesting and really cool. But I would actually say, I would kind of argue that a lot of the materials and technologies that we currently have are good enough. And I would say that really what needs to be done in the field are to find those kind of societal challenges, those commercial opportunities. And really the focus should be more on the systems level type implementation and finding effective methods to kind of adapt methods in kind of controls and machine learning and kind of human machine interaction so that these robots can actually do useful tasks in coordination with humans. And so I would say kind of a lot of the challenges at this stage are kind of more on the algorithmic side. It's not as eye-catching to me, as somebody who is kind of more of a mechanical engineer and kind of more steeped in the material science of it. But from our spin-off companies and just kind of, from where I am and just my academic research at this stage, I would say that kind of represents the bigger barrier. Yeah, and thanks for your email. I'll definitely reach out. We can schedule a time to chat.
And there's a question from Tarun about, have either of you seen bunches of rigid microbots that can self-assemble to perform different tasks? which we've seen in the microbots in Big Hero 6. And I have seen similar at SRI International with their microfactory. There's a couple of videos online, but I am not as up to date on the area of swarm or self-assembling robots as I think perhaps you might be.
Well, I'd say that that group at SRI, that project that you're referring to, they definitely kind of, are leading that space. I mean, they've done some really exciting work in that. There's been really cool work in magnetic miniaturized robots. And so these are magnets, basically ferromagnetic materials or permanently, or magnets that can kind of operate in swarms, and they can kind of self-assemble and kind of form kind of robotic systems. And there's been a number of research groups that have looked at that. Also, Radhika Nagpal at Harvard University has does some really cool work with these kind of swarm robots and having them coordinate to perform tasks. And I know one of her former PhD students, Kirsten Peterson, who's now at Cornell, has continued a lot of that research. And so it's a very rich field within the academic space. And I could kind of go on citing other faculty, but within the private sector, yeah, I'd say that SRI has done the most that I've seen, at least.
Well, that's great. And we've got a couple more links that people have put into the chat. And I was just thinking, I'd seen Assembler, which was a swarm construction robotics company coming out of Bristol Robotics Lab, which I know Sabine Howard, who had come from Radhika Nagpal's lab. In some ways, robotics becomes a small world, but you can see these influences moving over there. But I am very interested myself in construction robotics, and I believe that they had said recently that it was, how do you say, the swarm robots were a step too far for the market, that there were preliminary products that they needed to focus on in terms of the whole service or the software or the sensors that they could provide. And in ways we see this, we've seen things in factories where it's not the actual robot or the mobile robot with the arm, it's just the mobile robot, or it's just the sensors that are filling a big enough need to start off with, that the more sophisticated solutions that are possible just aren't marketable yet. And again, we're leading into this topic of commercialization. And I was really pleased that you talked about looking at these technologies moving into society, because there is a bit of a chasm going between the research lab to real world, which, I know a number of groups, including Silicon Valley Robotics, attempt to deal with. But I know we're also running out of time. You're on the East Coast, so it is much later for you. And I really thank you for staying this extra bit. I know Oren's put his hand up again. Do we have one last question? Can we fit one in?
I'm fine, yep.
Okay. Oren?
I did put one in the chat, but I guess it was just still up. Do you have any resources for silicone casting with use in soft robotics? That's a skill, but is there any resources or classes that I can take for that?
There are some online do-it-yourself resources, like instructables.com is a good resource. But yeah, I'm happy to, maybe when we schedule individual time to meet, I can point you to some others. Yeah.
And we actually had a really great Women in Robotics. We did a monthly hardware hack day before the pandemic, and Jessica Armstrong cast her own soft robot and got it working during the session. We're super inspired, and I'm really hoping maybe we can organize some soft robotics casting workshops at Circuit Launch. That would be a lot of fun. But I just want to really big thanks to Carmel Majidi and David Jaffe, and apologies for mispronouncing your name at the start. Those were fantastic presentations. I'm really inspired, and I want to thank you very much for sharing with us today.
Thanks for having us. It's been a pleasure.
I'm glad we had a little bit extra time.
I think it was worth it for sure. And I'm going to take that on board for the next events, totally. But really appreciate that. And I know it's getting very late for Carmel. So we'll say goodnight to everybody now. And thank you all for joining us.